Hello, my name is Nicholas Candello. This is my Physics 2212 video lab report number 2. An introduction to this lab. The purpose of the lab was to observe interactions between charged tapes and their surroundings, which could either be charged or neutral. Additionally, we're using measurements and observations to determine the quantity of charge of the tape. Some key concepts you need to know are how to calculate electric field and force using Coulomb's law, the superposition principle, which tells you how to calculate the net electric field and force of multiple point charges, the gravitational force, and the concept of distributed charges and how they are calculated. The results of this experiment showed that using the point charge model versus the line charge model yield substantially different results and have a wide range of accuracy between the two. So the key concepts on the left, you can see Coulomb's law for a single point charge and the conversion from that electric field of the point charge to the electric force. On the right, you can see the calculation for the force of gravity, which is defined by mg. And on the bottom right, you can see the principle of superposition, which shows that the net electric field of a distributed charge is just the sum of all the individual point charges. So the physical experiment for this lab involved 2 pieces of charged tapes, which are assumed to have the same quantity of charge. The 2 pieces of tapes are brought closer until the top one starts to levitate above the bottom one. Once that observation is seen, you measure the distance between the two, which is our distance of repulsion. And from there, you can set the force of gravity, which is calculated by mg, equal to Coulomb's law, and solve for the charge, which was calculated to be 2.8 times 10 to the negative 9th coulombs. The sources of error in this experiment are assuming that only the outermost layer of atoms is losing electrons, which is not true. And also we're ignoring adhesive tension with the table and the tape and normal forces from the mass of the tape on the table. So going into the computational model, first you can see here we define a function that can calculate the electric field of a charged particle at a particular observation location. At the top you can also see some of our constants, which include K, 99, gravity, and the mass of the tape. Moving down, you can see another function called line charge. This essentially defines the actual piece of tape as a collection of n point charges, and it creates spheres for every single point charge, gives them their mass and their individual charge based on the ratio of that point charge to the entire piece of tape. Now near the bottom you can see the created tape objects, which are 2 line charges. They are separated by the distance of repulsion, and they have n equals 10, which means they'll have 10 point charges each, with a total charge of q. Going on, you can see we go through every single charge in the top tape and calculate the electric field due to each individual point charge on the bottom tape. And then we do the reverse of that for every charge in the bottom tape. So we're calculating basically every single combination of electric field values between the top tape and bottom tape. Additionally, we graph the net electric field on the top tape due to the bottom tape, and we graph the force of gravity on the top tape. And you can see from this computational model, we calculate that the net charge on one tape is 8.7 times 10 to the negative 9th. So some experimental assumptions that could be made. In this experiment, only the bottom one is a valid assumption. So the first one is not valid because once the system is at equilibrium and the tape is floating, there is no velocity, and velocity is what incurs a air resistance force. The second one, we're treating the tape as a point charge, and that is not the case because in this experiment, we're treating it as a distributed charge with a collection of point charges. And the third one is an assumption we are making, since we're assuming that every preparation of a charged tape is done in the same fashion, exactly the same motion, which would yield the exact same charge, which is obviously not possible in the real world. Some additional questions. What if we had to model each of the tapes as a point charge? Compare the estimated value in that case in the point charge model to the line charge model. So the calculated charge using the line charge model was approximately 3 times the charge calculated using the point charge model. And then the second question asks, why do these estimates differ? They differ because of assumptions made by the point charge model that all the charge is centered in the tape. With the line charge model, electric field components are accounted for from every part of the tape, resulting in a much more accurate measurement of the total charge. So in conclusion, neutral masses can be induced with a charge by friction or other methods of preparation. Charged objects can interact with other charged objects and neutral objects. Objects can float if an electric force cancels out the gravitational force, and representing electric fields between objects as collections of point charges allows for much more precise measurements. Thank you for watching.